Okay, thank you. Good morning. I'm Tim Masterlark from the South Dakota School of Mines, and I'm here on behalf of the Magmatic Systems team. We began meeting last summer with some amazing folks all listed here. There are some serious heavy hitters on this team, and it was a great learning opportunity for me. And of course, I got asked to do this by my team. Thanks a lot to all of you. But the price of this is how many Magmatic Systems team people are out here? I know there's a couple. Don't be shy. Okay, well, the price of this is my ham-fisted interpretations of frankly some amazing ideas that came out of this group. So I'll do my best. So just as an overview, why are we interested in drilling for the Magmatic Systems team, or frankly, all of us here? And this is the only way we can get at that third dimension. We're all residents of the Earth's surface. We can see everything on the Earth's surface. There's satellites, thousands of them flying overhead. They can see every square inch of the Earth's surface as a function of time. But what about downward? Downward is a problem. So looking at the figure on the top right, I want to give you a little peek behind the curtain to the life of a professor. You can always tell when a professor is talking about something that has data, because their hands are at their side and they're talking about whatever topic it is. It might even come off as a little boring. But as we move to the bottom right, that's when the arm waving goes on. And so you can tell right away, is it conceptual? Is it these amazing ideas? There's lots of arm waving. But ultimately, the goal of this group is to go from the bottom right to the top right. Okay, but that third dimension, critical. Well, what about the fourth dimension? What happens down there inside the Earth as a function of time? And if you're going to ask that question, you really can't ask that question without first addressing the first one, the third dimension. So here we go with the Magmatic Systems team. I was actually very interested in joining this group, even though I have connections with the other groups as well. In particular, because the Magmatic Systems team can really nail the who cares question. Amazing science, going to drill a volcano. That's pretty exciting. It ties in with energy, geothermal, as well as the energy expansion and critical minerals. It ties in with hazards, of course, and it has this certain level of coolness. So when I tell my freshman geology students, sorry, no lecture on Wednesday and Friday because I'm going to Washington, there's that, yeah, no lecture. That's great. And students being students, they always have an angle, always trying to push the envelope. So what are you doing in Washington? So I told them, well, I'm going to talk to some colleagues out there and meet with some government agency officials to talk about drilling into a volcano. And resounding thump as jaws hit the floor. Then that moment of silence, and then I could feel my street cred as a scientist. Through the roof. Okay, so anyway, as a group, we came up with 4 frontier themes: volcano stratigraphy and structures. What do volcanoes look like on the inside? And what does that structure look like as it evolves through time? Number 2, magma storage and plumbing systems. What's the magma doing down there? What's the pressure? What's the temperature in the crust? What does it do as a function of time? And then look at the rheology of the crust. As we go from the land surface, they simply vertically going down through those materials and finally intersect the magma chamber. It doesn't just go from rock to magma. There have to be some amazing things that happen as we go down in that direction. Number 3, how do volcanoes tie into geothermal systems and ore deposits? So the volcano magmatic system, the source of heat, source of volatiles, the source of materials, and that heat is going upward into the crust full of fluids. Some of those volatiles from the magma get into those fluids. How do they interact? This has everything to do with geothermal systems, as well as those ore deposits, those chemically active hot fluids rise. They're buoyant. They're dissolving materials out of the country rock. They rise, they depressurize, they cool, and they deposit materials, ores, ore bodies. So number 4, finally, faults in magma. Looking at magma, changing the pressure temperatures of magma. How do we change the stress, the pressure, the fault friction, the rock properties, all of these as a function of time for nearby faults? And so how does that change fault stability? How does magma trigger earthquake activity, or how do earthquake activities change the stress, the pressure, and all of this of the magmatic system, and possibly influence the magmatic behavior at depth. So these are 4 theme topics, and I'll dig a little bit into them. And then as a bonus, we'll talk about some frontier resources that we might think about as we go after these 4 themes. I'll touch on some potential drilling projects, and then I'll end with looking at how does this group integrate with the other drilling groups. So for starters, volcano stratigraphy and structures. So we can ask some pretty important foundational questions. What does that magma supply look like over time? Why does the magma composition evolve? And when we look at observed rocks, how can we relate what we see at the surface or even in rock cores to the source of that magma in the mantle? This is an example of Savati Island in Samoa. There's a workshop going on with this right now, so this is an active project. But this is a case of an island, hotspot volcano, moving with the Pacific plate. The timing of the Samoan arc is in correspondence with Hawaii volcanoes. And when we think about Hawaiian volcanoes, that's the one that gets all the attention. It's the case study. We know everything about Hawaii. That's great. So that means we know everything about hotspot volcanoes. Well, that's the general thinking, but that couldn't be further from the truth. So Samoa, same timing, hotspot volcano, oceanic crust theme, very different magmas, very different stages in its evolution. What's the cause of that? So here's Samoa, here's the Tonga Trench. We can see this trench rolling back as a function of time. So first order hypothesis, the difference between Samoa and Hawaii is Samoa's proximity to this subduction in this trench. I made that hypothesis up like just now, but nonetheless, that's one hypothesis, and you can start rattling them off. So you want hypothesis-driven science. It's not too hard to come up with really interesting ideas that could be tested with drilling. Theme number 2, magmatic storage and plumbing systems. So what does the magma pressure and temperature look like in the crust and the rheology of the crust? Key questions: reliability of geophysical models and magmatic systems. So we can see down there sort of with geophysical information gathered at the Earth's surface. And so here's an issue that we came across with. This is Magmatic volcano in the Aleutian Islands. This is INSAR data. We can see the volcano moving down due to magma coming in and replenishing its magmatic system at depth. We have seismic tomography. These are little slices with this footprint of rock properties. Blue is strong, weak, and red is weak. We can build a numerical model that simulates pressurization of a magma chamber in a domain that accounts for these rock properties, and we can predict the deformation really, really well. Awesome. Or we can do the same model without these rock properties and just put a constant value of, say, basalt for the whole model, fiddle with the model parameters, and predict the data equally well. So what have we learned? We're predicting the data, but what have we learned? And the answer to this question is, well, you can figure out how important these properties are, or even if these are even true, what should it look like if you drill that volcano? Additionally, not just the rock properties, but also the rheologic properties. Is it brittle? Is it ductile? Is it something in between? We can, little peek behind the curtain, number 2, we can always simulate the data in geophysics by fiddling with adjustable parameters. But we're always led back to that question of, yes, but how reliable is it? And what have we really learned? Number 3, geothermal and hydrothermal systems and deposits. So these two clearly fall into that class of arm waving. I'll try to keep my hands down. But key questions, we're looking at fluids: temperature, pressure, composition of the fluids, hot body, hot magma body, fluids rising here, dissolving materials down here, rising, cooling, precipitating, new materials, lots of things going on, changing the composition of the fluids. Likewise, we're changing the composition of the rocks as we move those fluids through the rocks. So lots of things happening here as a function of space and time. All of this is conceptual, and without drilling, we really have a problem. So here's an example that we could use. A straw man target, a target like Yellowstone, but not Yellowstone, because we can't do that. But we're looking at reflectivity, PZP, PZS, clearly identifying the top of the magma chamber at this depth of about 3.8 kilometers. And it has the bonus of, in order to get this kind of signature, I'm told that magma chamber has to have supercritical fluids in the magma body as well. So we can see this with geophysical data, but how reliable is it? And is it true? How can you answer that question? Drilling. Drilling will get you there. Faults and magmas. How do these magma bodies interact with the stress and pressure fields of surrounding faults to act as stabilize or destabilize them? This is an example of the COSO geothermal field in California, before geothermal production, after geothermal production, and the little red boxes represent seismicity. So you see seismicity in here, little red boxes. Started producing, injecting, and withdrawing fluids in the system for geothermal production. And what they found was that there was this zone here where the earthquakes stopped, and earthquakes continued in these other zones. So we built a poroelastic model to simulate, well, it also included temperature as well, but to simulate, these are the observed seismicity changes, and these are what we predicted. And there's some encouragement here. We're able to predict with blue fault stabilization rather than destabilization, which is stabilization, which is what you see here. When we think about fluid injection, hydrothermal production, and people say induced seismicity, let's forget that it's not just induced seismicity, it's really about stabilization or destabilization of fault systems as a function of time. And that can go either way. So meaning production could stabilize fault systems. It doesn't always have to lead to earthquakes. This is another take on the interaction of faults and magmas. In the big picture, in a tectonic or geologic long-term context, looking at the spine of South America, the southern part, classic subduction zone going on here, and volcanic arc here. The question is, there's a fault, and there's a fault that takes up oblique convergence from this subduction zone. The fault runs right through the magmatic system of volcanoes. So the question is, are the volcanoes controlling the location of the fault, or is the fault controlling the location of the volcanoes? And this is just one example, and the answer to that question might be one way here and another way somewhere else. But nonetheless, in the big picture, we can start looking at where do volcanoes form in the first place and tie them back to big plate tectonic plate boundaries and earthquakes. Okay, so those were the 4 frontier themes. Frontier resources, lessons from the energy expansion. I'm using the word energy expansion rather than energy transition, and that is intentional. And the reason is we're expanding our energy needs. Natural gas demand globally is at an all-time high. That's not going away. So calling it energy expansion, we can argue about that over coffee or the cash bar this evening, but I'm in charge, so I put it up there. Anyway, key questions. How can we benefit from industry and all the things they've learned in the past several decades? So let's go back to fracking. We don't have to think about drilling as a vertical hole anymore. We don't have to think about drilling as an oblique hole or a hole that goes down and turns. We can now start to think about drilling as, well, maybe there's a drill pad up here that goes down and it branches out with pin 8 drilling and then breaks off into even smaller. Now, there's a lot of cash that goes on here, but the technology exists. The technology exists because we're willing to innovate. So I want to illustrate this with hydrogen underground storage. I got involved with storing hydrogen in underground salt caverns. We do this for petroleum and other petroleum gases all the time, frankly. But can we put hydrogen underground to store it long term? And this comes back to the energy expansion. And the idea was you could use solar or wind at the land surface to crack water, make energy, oxygen, and produce electricity for when the sun is shining and the wind is blowing. But then take that hydrogen, put it underground so that it acts like a long-term battery. So when the wind is not blowing and the sun's not shining and you need energy, then you can pull that hydrogen and burn it as a source. Well, sounds great. But the lesson here is that there was hydrogen, H2, it's a tiny little molecule, and it's really reactive. So they couldn't just use standard drilling casing steel. So they had to do new steel formulations. They had to innovate. It cost money, but they innovated. They have now new steel and realized that standard threaded couplings aren't going to work because that hydrogen can get in there and leak. So they have to weld. Well, the cost goes up, but it can be done. Okay, so they were willing to innovate, and it looks like this is something that's now on the table and will be happening. So I want to extend this to, here we are. This is an example of Augustine volcano. Magma body down here, some standard geothermal situations here. That's great. Okay, but what if we innovate? And what if we're willing to innovate and start drilling in extreme conditions? High temperatures, high pressures, acidic fluids, really nasty things. And instead of getting this hydrothermal source, we go for this one, which has way more energy. Now, it has a high risk and a high cost investment, but it also has a high societal potential reward. And there's a poster, at least one poster about this topic somewhere here. Here are some examples of drilling targets. So I mentioned Augustine volcano, when there's this idea here that we move to the right-hand portion of this diagram by drilling hot, shallow depths. There will be an investment to innovate to make it happen, but imagine the results. I mentioned Samoa, and there are other hotspot tract volcanoes here, that any number of them that we could study and ask these questions. How are they different? Why are they not the same as Hawaii? Or why are some of them similar? I don't know. But nonetheless, many, many questions we can ask. This is a great example from the Western Alps. This is an arm waver. Absolutely love it, though. There's all kinds of things going on in the system and all different sorts of rocks. And it's amazing, this super volcano. Really exciting stuff here. And I'm not trying to marginalize this. I'm saying there's exciting opportunities to learn some fantastic geology that describe the inside of the super volcano as a function of space and time. And finally, cross-pollination. So with magmatic systems, we're looking at geothermal energy. Well, that has the obvious tie with the energy expansion. Geothermal ore deposits. Well, this ties with energy expansion and critical minerals that are needed for electronic devices, batteries, and these sorts of things. Magma, earthquake, stress coupling. We can easily tie that with the faults and earthquakes community. Life in extreme conditions, the geomicrobiology. Well, if you're drilling into a volcano, you're looking at life conditions as we go from high temperature, pressure, and maybe chemically unfriendly type environments to us, but we can look at what does the life look like as we go down. Volcano stratigraphy and eruption history. This ties into paleoclimate climate and paleoecology. Over breakfast, I didn't have the chance to ask my colleague, do you see little ash layers in your lake sediments when you drill through them? I would imagine you do, but that's pretty cool because you can start tying that to volcanic eruptions and a variety of other things. I missed the hydrology and the critical zone here, but the whole point of this at my first slide was talking about drilling from the land surface into the volcano. So I think we got the critical zone covered. Yeah. Okay. Maybe not. Okay.